Hello. In this video, we're going to continue on the topic of differentiation, but of course, it's going to be more interesting. So I'm going to introduce a bunch of consequences of mean value theorem, right? Which is a very important theorem. Let's just give a really quick review on what we have done on the topic of differentiation. So the first thing, I introduced the definitions, and then we proved some, for example, the derivative of summation of two functions, product of two functions, division of two functions, and we also proved the chain rule, right? And then if you watch the second video, we have talked about some examples, and we also introduced the definition of local maximum, or of course you can think about local minimum, right? They are pretty similar. And then after that, we introduced a very important theorem. I think it's very important because it is used in the proof of mean value theorem. So the theorem is that if you have a function defined on closed interval AB and mapped to real line, and if x is local maximum, where x is any point in the open interval AB, and if we also know that f is differentiable at x, then we know the derivative of f evaluated at x must be equal to 0. So in my opinion, in the proof of generalized mean value theorem, which we proved first, we created a kind of like a new function h, and we can translate our problem recall the statement of the generalized mean value theorem. It is like fb minus fa times g prime of x is equal to gb minus ga times f prime of x. So it's really a statement about function f and g, right? But in the proof strategy is we create a new function h, and we want to prove some properties, some nice properties of h, such that it is equivalent as our ultimate statement about f and g, right? So that is very common trick in real analysis about translating our problem into a different one and focus on the new function h, for example. And then in that case, we actually use this theorem about local maximum and derivative of x, derivative of f evaluated at x equal to 0. So if you recall, we did use the theorem of a local maximum and its derivative equals to 0 in the proof of generalized mean value theorem. So I just want to emphasize the proof strategy, and also just give you a really quick review on what is generalized mean value theorem. And then what we did is we, based on the generalized mean value theorem, we proved the common use mean value theorem, right? Which is very short. The proof of that is very short because we just apply the generalized mean value theorem while making the function g to be gx equals to x. So that's basically, that's it for the proof of mean value theorem. And we discussed a little bit that the importance of the conditions for the mean value theorem. So it is very, very important to have your conditions right. For example, the first condition is, of course, we are based on the context that we have a function f defined on closed interval AB and mapped to real line, right? So the first condition is f is continuous on the closed interval AB, and the second condition is f is differentiable on open interval AB. So we have proved at least on open interval AB, and we give some counterexamples to show that when a function does not satisfy those two conditions, the mean value theorem will fail. So it's giving conditions. And today, what what we are going to do is, because it's a very important theorem, right? And it has a lot of consequences and they are very interesting. So I'm going to introduce some small consequences that you must have seen them in your calculus classes. And then I will prove two major theorems, which is L'Hopital's rule and the Taylor's theorem. So I was very excited to review the proof two theorem, and I think I still gain a lot nowadays that by just I still gain a lot about the insights of the real analysis proof strategy. So let's get started with some simple ones. Okay. So the first is a corollary. We could just call it corollary. If your function is defined open interval AB and map to R, and it's also differentiable on AB, then if the derivative at x is negative, larger or equal than 0, then f is monotonically non-decreasing. So I think, sorry about the unclear statement. I think what I'm trying to say is strictly larger than 0. So if the first derivative of f evaluated at x is strictly positive, then f is monotonic increasing on AB. And here I mean strictly monotonically increasing on AB. And if the derivative at x is equal to 0, then f is constant on AB. And if f is the derivative at f where AB is smaller than 0, monotonically decreasing. Sorry, I feel like I did not state the statement in a very clear way. So what I mean is this quantifier out for x. So when we say, first off, when we say f is monotonic increasing or constant or monotonic decreasing, it is not about one point, right? If you say a function is increasing, you must compare the function f, the value of function f at multiple points. So that's why I think what I said at the beginning is incorrect or very misleading. And I apologize for that. So what I'm trying to say for this corollary is, given that the derivative of f for all x on this interval AB, if for every point on this interval, the derivative of f is strictly positive, then we know the behavior of function on this interval, which is monotonic increasing. And similarly for constant, if we have the derivative of f is equal to 0 for every point on this interval, then f is constant on AB. And if the derivative of f is smaller, strictly smaller than 0, for every point on this interval AB, then f is monotonically decreasing on AB. Okay, I hope that's clear. And let's prove this quickly. So the way we're going to do is, so it is consequence of mean-value theorem, right? And then if you recall mean-value theorem, I mean the common use one, which is the simpler, where f is the simpler version where gx is equal to x. So if you recall the mean-value theorem, the statement is basically fb minus fa is equal to f prime of x times b minus a. So if you look at the statement, it involves with, first of all, the function f evaluated at 2 points a and b. And then the second is the derivative. There exists x, one single point x on the interval ab, and we evaluate the derivative at that point. And we also have the component that b minus a, which simply is the, you can think about it as a distance in the distance of interval ab. So if you recall the definition for monotonically increasing is, for example, x is whenever x2 is larger than x1, fx2 is larger than fx1, right? So right now you must have like intuition about how to prove this because we can utilize the mean value theorem. So I can write this as so the mean value theorem is x1 minus x, sorry about that, x2 is equal to f prime of let's call it x2 minus x1, right? So if we want to show our functions monotonic increasing, given that x2 is minus x1 is larger than 0, we want to show this is larger than 0, right? So want to show. And how to show this? Well, we just need to show this is larger than 0. So that is our goal. And that's basically what we're doing in this proof. Okay, now let's look at the proof. So suppose that x2 is larger than a, smaller than x1, smaller than b. Sorry for the notation, it is a little bit inverse than what I wrote before. So in our proof, we actually assume that if this is the line, this is a, this is x2, this is x1, this is b, right? So we're doing something like this if you want to show the monotonic increasing behavioral function now. Okay, and then we want to apply this, right, on the interval, right? So x2 is before x1. The first thing during your proof, when you have an idea about what theorem you want to apply, that's good. And the next thing is to check the conditions so that you can really apply the theorem, right? So there are two conditions for mean value theorem. One is continuity, one is differentiability. And recall, one is on the closed interval, one is on the open interval. Okay, and we want to prove f had that. F satisfies those conditions, right? So since we're given f is differentiable on AB, we know f must be continuous on AB. And because the interval x2, x1 is a subset of AB, and f is continuous on AB, so of course f is continuous on this interval, this closed interval. And meanwhile, because f is differentiable on this interval AB, open interval AB, f must differentiable on the open interval x2, x1. Therefore, okay, the condition checks, and therefore using the mean value theorem, we have the existence of such x in this interval x2, x1, such that f satisfies this equality, right? And then because for example, let's prove statement 1. We want to show f monotonic increasing on AB. To show that, we assume x1 is larger than x2. So we have this positive. And then we use the assumption. So here we have assumption f prime of x larger than 0 for every point x on AB. And notice that there exists x on this interval, which is subset of AB. So x here must be an element in the interval AB. And based on our assumption that f prime of x is larger than 0. So we have the whole thing that is non-negative, therefore difference must be non-negative. And therefore f is monotonic increasing. Right, so let me just do strict increasing or strict decreasing. And the similar argument works for the statement 2 and 3. So this is always positive, and if we assume this is equal to 0, then the whole thing is equal to 0. Therefore, this is equal to 0. So when x is equal to x2, fx1 is equal to x2, therefore f is constant. And because this is larger than 0 and this is smaller than 0, which is our assumption, the whole thing is negative or non-positive, right? So, right, I forgot I want to do strictly. So, so this is strictly less than 0. This is strictly larger than 0. So together they're strictly less than 0. So therefore, they're strictly less than 0. Therefore, this is strictly less than 0. Let me change that. And therefore, the function f is strictly decreasing. You can say strictly monotonic, decreasing. And therefore, we proved our theorem. So that's, I don't have anything else to say about the corollary. I'm sorry about the inconsistency about strictly increasing or just increasing. But at the end, I actually change the statement and the proof to strictly increasing or decreasing. Right, I need to make this also strictly. Okay. The second consequence of mean-value theorem is, so if you have two functions f and g from R to R, and they're differentiable and non-vanishing everywhere, which means at every point on R, f and g evaluate at every point on R, the value of those two functions cannot be equal to 0. So when we say vanish, which is basically means 0. Okay, and another assumption is f prime is equal to x and g prime is equal to g. Then our conclusion is f is equal to c times g, where c is a constant. This could be useful sometimes, but I think I have seen this in my calculus class, and I don't see this is used in any of the proof later. Not as useful as the local maximum and the derivative of the local maximum equal to 0. Useful. But let's look at the proof. It's short. So I'm gonna highlight with pink highlighter. Whenever I see this device is used in the proof. So which device? I mean, when we have a problem statement and we translate that problem statement into a new problem statement and we focus on that. So here we have a problem statement about function f and g, and we translate it into function h, and we focus on proving some nice properties of function h. So whenever we encounter that, I'm gonna highlight that in pink. Okay, since f and g are non-vanishing everywhere, so so gx, which at the bottom, can never be 0. Therefore, this expression is defined all the time. No worries. Now we claim h prime of x equal to 0 for every x on R. Why do we want to do this? So again, it's like a translation of our problem, and I'm going to explain why we can translate this. Because when h prime of x is equal to 0, we know by previous corollary or proposition that the function h must be constant. Like whenever its derivative 0, then the function must be constant. Okay, and then when h is constant, that means f over g is a constant. Therefore, f is equal to c times g as desired, right? So what is left to show is h prime of x is equal to 0. And how to show that? Well, we just write down the definitions, or we just write down, this is the division rule that we proved in the first video. So h prime of x is equal to g times f prime minus f times g prime over g squared. And because f prime is equal to f, g prime is equal to g, we can just plug in, right? So we replace f prime with f, and then we replace g prime with g, and then of course numerator becomes 0. Therefore, the whole expression for h prime of x is equal to 0, and we're done. Okay, so the next thing is the next consequence of mean-value theorem is I call it intermediate value property of derivative of functions. So what we're doing here is, so suppose f from closed interval AB to R is differentiable on AB. And of course, when I say differentiable on closed interval, I really mean at the extreme, it is one-sided limit. And then we have a assumption that f prime of A is smaller than lambda, smaller than f prime of B. So lambda is a value between those two values. Then the claim is there exists an x, a point x on the open interval AB such that f prime of x is equal to lambda. So if you recall the intermediate value property, so I think what I mean to say here is property, right? What is that? So when we are given a function, and if we have a value between GA, GB, where AB are the boundary of the domain of function G, then there exists x in the open interval AB such that gx is equal to lambda. Geometrically, I can write really quick. Like for example, if I have a function like this, and of course it is defined on AB, right? And then now if I pick a point lambda, let's call it lambda, right? And it is between GA and GB, right? And then the intermediate value property is saying that, okay, there must exist a point x between the open interval A and B such that gx is equal to lambda. And what we learned in previous, I think in the 140A real analysis, the first series of the real analysis series is, sequence. We have 3 sequence of real analysis, and the first sequence talks about intermediate value theorem. So what we know, or what is well known, is that if function is continuous, then G must have intermediate value theorem property. Notice that I want to emphasize here that continuity is a sufficient condition for IVT property. It is not a necessary condition. And that means this is one way. So you see this if and then, right? That is not only if, which means if a function has intermediate value property, we cannot guarantee that this function is continuous. So as I said here, there are many discontinuous functions has the IVT property, but they are not continuous. So it is good to point out here that the intermediate value property of f prime does not imply f prime is continuous. So you cannot say that if I have a function satisfy those 2 conditions, then this function is continuous. No, that is not what we're saying, and it is not incorrect. It is incorrect. So I will say here is if a function satisfies those 2 conditions, it has this, which is intermediate value property. And what is this term good used for? Is to check whether or not a function is a derivative of another function, because if it does not have intermediate value property, then it is not derivative of function. Okay, so let's just give a counterexample about, so if you have a function hx is equal to this, notice that, and we want to use the previous theorem to check whether or not this function h is derivative of a function f, right? And then if you look at the theorem is telling you that, okay, let's check whether or not it has the intermediate value property. If it does not, then we know for sure it is not a derivative of function. And notice that if it is intermediate value, if h has intermediate value property, we cannot say it is derivative of function f, because this implication is just one-way implication. So this theorem is really used for when you show a function h, for example, does not have intermediate value property, then h is not a derivative of any function f, for sure. And that's when you use this correctly. Okay, so let's see how's h. So h is defined in a piecewise function, and we wonder this question, right? And we claim no. Why? Because it does not satisfy the intermediate value property. And why? Because if you pick a point between 0 and 1, which is lambda here, you see there's no point on the real line that hx is equal to lambda. So therefore, using the previous theorem, h is not derivative of a function. Okay, so we introduce the motivation of the theorem, and we introduce how to use this theorem, and now let's prove the theorem. And how do we prove the theorem? So our goal is to show that there exists x such that f prime of x is equal to lambda, right? Again, so you see that I highlight this in pink. So we're doing the strategy again, which is translating our problem into a different problem. Here we have our statement in terms of I prime is equal to lambda, but we can actually translate into a problem associated with function g, which is defined in this way. So because we want to show this, right, and then g is defined in this way, and you can see, I hope you can observe that this statement is equivalent as g prime of t, sorry, g prime of x is equal to 0. So we want to show there exists x in AB such that g prime of x is equal to 0. And what does that remind you? What theorem do you want to use if your goal is instead g prime of x is equal to 0? You recall in video 2, local maxima, right? And the derivative at local maximum is equal to 0. So we want to use that. And actually I write down here lecture 2. So instead of showing this, right, we just show its sufficient condition, which is we want to show g has local maximum at a point x in open interval AB, and then g is differentiable at x. And so let's show the sufficient condition, right? And then we're done. So first of all, because f is differentiable on the closed interval AB, so g is, because g is defined in ft minus lambda t. Also, since f is differentiable on AB and f is continuous on closed interval AB, therefore g is continuous on closed interval AB. Why do we want to show that? Because the closed interval AB is compact. Therefore, if you recall, I don't remember exactly which chapter in baby rooting, but continuous function on compact interval assumes maximum and minimum. So here we want to show, so here we guarantee that there exists x on AB such that x is equal to the minimum of g. One problem. So, well, at here, you might think, oh, okay, we have so far gathered the information that g has a local minimum and g is differentiable at x because g is differentiable on AB and point on AB. Then we're done. We can apply the theorem and g prime of x is equal to 0, we're done. However, here I actually highlight in red that we must show that x is in open interval of AB. This is very important, and I think I gave a counterexample how this theorem fail if you don't satisfy this condition. So the rest of the theorem actually focus on proving this x we found. This x is not equal to A nor B. Okay, so where I stay here. And recall that if you look at this theorem, we haven't used this assumption yet. We have not used yet, and then we're going to use this. And let's see. So another observation is g prime of A is equal to this, g prime of B is equal to this. And because we have this assumption, and if you subtract lambda on both sides, eventually we have g prime of A smaller than 0, smaller than g prime of B. And that tells me that the derivative of g evaluated at A is negative, which means the red line I draw here, and where the blue line is function g. And g prime of B is positive, which means the slope here at this point is positive. So I drew here. And intuitively, well, sometimes when you, before you prove anything, you want to draw to give you an intuition, right? So here, it actually means that, sorry, my Apple Pencil just died. So it actually means here that it gives you an intuition that there exists a point on this blue line that is smaller than GA and GB. Okay, because it will go down first, right? Like from the left, it's going to be go down first because the slope is negative. And on the right, it's going to, if you look at the graph from right to left, it also goes down first. So what I want to say is intuitively, it makes sense that there exists a point that is even smaller than smaller value than GA or GB. But we want to prove, of course, we want to prove it rigorously. So since G prime of A is smaller than 0, we just write down the definitions, right? And then here the definition for G prime of A, and this is smaller than 0. And by definition of limit, right? There exists T1 in the neighborhood of AB such that the whole thing is smaller than 0. And because T minus A must be positive, so we can just directly write the numerator is less than 0. And similarly, because we have this and write down the definition, we have the limit of this expression is larger than 0. And write down the definition for limit is there exists T2 in this neighborhood. Well, you can call it neighborhood. Such that this is smaller than 0. Notice that we have this is larger than 0, right? So as t getting closer to b, there exists t that this expression is larger than 0. And notice that b is always larger than t, so the denominator is less than 0. And therefore, in order for this to be larger than 0, this to be smaller than 0. That's why I write there exists T2 such that GT2 is minus GB is less than 0. Okay, now we have those two information, and then rewrite it, we have this information. And so the logic is, okay, recall what is our goal. Our goal is to show that x, which is the minimum of the function g on the interval AB, is neither a or b, right? And what is definition for x? It's the minimum of the function g on the interval AB. Therefore, as long as we show there are points below GA and GB, we're sure that X must be below GX must be below GA or JB, because GX is the lowest possible point of function G on the interval AB. So here we grab those two, we show the existence of G1 and G2, and we know from our assumption here, we derive that the value of T1, the value of GT1 is less than GA, the value of T2 is less than GB, and therefore GX, which is a minimum of G, right, is less than, it must be less than GT1 and GT2. Therefore, GX is strictly less than GA, strictly less than GB. Therefore, GX, therefore X is not equal to A or B. Okay, so we will see this more in later proof of other theorem. So that's why I kind of like highlight here and did a little summary about this proof strategy. Okay, so in sum, we have shown that existence of the local maximum. I think here I need to say the local minimum of G, right? And this. And G, we know is differentiable, and therefore we can use this theorem. Actually, we use analog theorem, which is local minimum, but this is still equal to 0. Therefore, we have the G prime of X is equal to 0. And therefore, we're done based on how we translate our proof, our problem state in the beginning. The next two are more important that we use more often. One is L'Hopital's rule, the other one is Taylor's theorem. I will make a second video for this notes because I think it's a little bit longer than I thought. If you're interested, check out the next video. So thank you for watching. If you see any typos or mistake, please let me know. Bye.